Unimolecular nucleophilic substitution and experiment notes. In this webcast, we will discuss the background of the unimolecular nucleophilic substitution, or SN1 for short, reaction that you will perform. In this experiment, you will be performing a unimolecular nucleophilic substitution, or SN1 for short, reaction. As you learned in Chem 232, there are several different types of substitution reactions, and how they are different is their mechanism. To begin this webcast, we will have a review on substitution mechanisms. A bimolecular nucleophilic substitution, or SN2 for short, reaction is a one-step concerted transition state that results in inversion of stereochemistry. Let us break this description into smaller pieces. Bimolecular means that in the rate-determining step, we have two species that are reacting with each other. In this particular example, we have this alkyl halide and this chloride ion. They react in a single step through what we call a concerted transition state. In this transition state, we see that the chlorine atom-carbon atom bond is beginning to be formed at the same time that the carbon atom-bromine atom bond is being broken. This is what we mean by concerted. Everything is happening at once. The consequence of this mechanism is that our nucleophile, in this case our chloride ion, can attack this carbon from only one direction, from the opposite side of the bromine atom. This results in inversion of stereochemistry, where in this example our bromine atom was pointing towards us, therefore our chlorine atom must be pointing away from us in the product because it had to attack from the opposite side of the bromine. Not all substitution reactions will proceed through this mechanism. If you would like an SN2 reaction to occur, there are ways that you can bias the conditions to favor an SN2 mechanism. Primary leaving groups tend to be excellent candidates for an SN2 mechanism, followed by secondary leaving groups, and then finally by tertiary leaving groups, where tertiary leaving groups, for all intents and purposes, do not undergo an SN2 mechanism. This is easy to rationalize. If our nucleophile has to come from the backside of our leaving group, then the less stuff around the leaving group, the easier the reaction is. A tertiary leaving group has a lot of stuff around it, therefore it is very difficult for a nucleophile to attack it. In contrast, a primary leaving group is pretty open, and so is easy to attack. Strong nucleophiles tend to favor an SN2 mechanism. The reason for this is strong nucleophiles tend to react quickly. Why would reacting quickly help to favor an SN2 mechanism? To help answer that, let's first discuss the SN1 mechanism. An SN1 mechanism is a unimolecular two-step mechanism that proceeds through a carbocation intermediate. Consider this tertiary alcohol. We're going to add a little bit of acid. What this does is this turns this hydroxide, which is a terrible leaving group, into a good leaving group, and we'll talk more about this on the next slide. After being turned into a good leaving group, in this case water, we get spontaneous breakage of this carbon-oxygen bond, producing water and this carbocation intermediate. We have a carbon here, which has only 3 bonds. Therefore, it is positively charged, and we have this wide open MTP orbital that is a fantastic electrophile for a nucleophile to attack. In this case, the bromide ion that formed after HBr was used to protonate the alcohol. Our bromide ion attacks the carbocation to form our final product. Let's talk about how this is a unimolecular mechanism, but it's 2 steps. This might sound like a discrepancy, but these 2 adjectives describe different aspects of this mechanism. The unimolecular portion refers to the rate-determining step. Remember that in a mechanism, the rate-determining step is the slowest step. In an SN1 mechanism, the ionization step, this first step to form the carbocation, is the slow step. In this step, the only species present is this alcohol. Therefore, this is a unimolecular rate-determining step. This is in contrast to the SN2 mechanism, where the rate-determining step is the only step, the attack of the chloride onto our alkyl bromide, where we have 2 species, therefore this is a bimolecular rate-determining step. If we return to the SN1 mechanism, this is a 2-step mechanism because it takes 2 steps to go to product. The first step is the ionization, And the second step is the attack of the nucleophile onto the carbocation to form our final product. Let's say we wanted to favor an SN1 mechanism. How could we do that? Well, the key difference between the SN2 mechanism and the SN1 mechanism is the formation of this carbocation. Therefore, if we want to favor an SN1 mechanism, we should choose conditions that make forming the carbocation easier. One way to do this is through substitution of the leaving group. Tertiary leaving groups are better than secondary leaving groups, which are better than primary leaving groups. This is because the more carbon atoms connected to the carbocation, the more stable this carbocation is. Primary carbocations are so unstable as to not exist, whereas tertiary carbocations are actually fairly stable and easy to form. We can choose weaker nucleophiles. Why would weaker nucleophiles help us? These would help us because weaker nucleophiles are slower to react. If this ionization step is slow, then using a weaker nucleophile means we have more time for this step to occur. For an SN2 mechanism, I said we wanted strong nucleophiles. The reason we want strong nucleophiles is because a strong nucleophile will not wait for a carbocation. And finally, we can choose solvents that stabilize the carbocation intermediate. By choosing solvents that are polar protic, we can help stabilize this high-energy carbocation and make it easier to form. Before we continue, a discussion on stereochemistry that results from an SN1 mechanism. You will notice that this carbocation is trigonal planar in geometry. It is flat. That means our nucleophile can attack from either the top or from the bottom. In this particular case, our starting compound was not chiral. But if this starting compound was chiral, the consequence of this reaction is that we would make a mixture of stereochemical products, because there is no preference for one side of the carbocation over the other. Now let us show this mechanism in action. You will be taking T-amyl alcohol, also known as 2-methyl-2-butanol, and exposing it to hydrochloric acid. What will happen is the alcohol will be protonated using the acid, to form a much better leaving group. Before we continue, to be clear, this first step, the protonation of the alcohol, is not part of the SN1 mechanism itself. This first step is simply to convert our alcohol into a good leaving group. Notice how I've drawn equilibrium arrows here. This protonation step is reversible. We can protonate this alcohol and then subsequently deprotonate the protonated alcohol in many cycles. Of course, if this is all that happened, this would not be a particularly useful reaction. Once the alcohol is protonated, we can begin the SN1 mechanism portion of this reaction. Remember, in an SN1 mechanism, we go through a carbocation intermediate. To make that intermediate, our leaving group is simply going to leave. To form our carbocation. Chloride ion that we had formed previously, after using the hydrochloric acid to protonate our alcohol, then acts as a nucleophile and attacks the carbocation to form final product. It is these final two steps, the formation of the carbocation intermediate on the bottom and the nucleophilic attack of the nucleophile onto that carbocation on the right, that are the two steps in the SN1 mechanism. Remember, the initial protonation is not part of the SN1 mechanism proper. The protonation simply forms a good leaving group. The SN1 mechanism itself is the formation of the carbocation and then the nucleophilic attack onto that carbocation. So, not too difficult. We have a terrible leaving group, this alcohol, which we protonate using acid to turn it into a great leaving group. Our leaving group then leaves of its own volition to form a carbocation, which our nucleophile then attacks to form our product. A few notes about drawing mechanisms before we continue. Notice how all of my arrows start either on lone pairs or on bonds, and they end on atoms. Remember that a mechanism shows the movement of electrons, not the movement of atoms. Arrows start on electrons, either lone pairs or bonds, and they end on either atoms or bonds. In this experiment, you'll be adding T-amyl alcohol, also known as 2-methyl-2-butanol, to your separatory funnel, and with it you'll be adding a concentrated hydrochloric acid aqueous solution. You will then shake these two things together to what we call affect the reaction, or in other words, cause the reaction to occur. One note before we continue. T-amyl alcohol is a liquid. The concentrated hydrochloric acid solution is a solution. In your physical properties table, you do need to record the number of moles being used for each component here. Remember that for a solution, you have to use the concentration to find the moles. Whereas for a liquid, if you are measuring a volume, you have to use the density and then the molecular weight. You will then identify which layer is which. One layer will be your aqueous solution, and one layer will be your product. Think back to the extraction experiment. How can you identify which layer is your aqueous layer and which layer is your organic layer if you don't know which one is which? Speaking of the extraction experiment, you will then use the skills you learned in that experiment to purify your product. You will perform what we call a wash. A wash is simply a type of extraction. Specifically, a wash is usually trying to remove impurities from the organic layer. The first wash you will perform is with aqueous sodium chloride solution, what we call brine. The purpose of using a brine solution is to remove any bulk water located in your organic layer. Remember, organic solvents always pick up at least a little bit of water. What a brine solution does is, in the same way that biological cells can have water leave or enter them as a result of salt concentration inside or outside of the cell, a brine solution is saturated in salt, and as a result, any water in the organic layer will leave the organic layer in order to dilute the salt in the aqueous layer. Once you have removed any bulk water present, you will then add in an aqueous solution of sodium bicarbonate in order to remove any remaining acid. Remember, sodium bicarbonate is a base. Once you have performed these two washes, these two extractions, you will then take the organic layer and completely dry it using drying agent, like you did in the extraction experiment. And finally, you will purify your product via a distillation. At the end of the reaction, it is likely that you'll have a mixture of at least your product and unreacted starting alcohol. You will use distillation to separate them. A quick note on extraction before we continue. Sodium bicarbonate, being a base, will react with hydrochloric acid. In this process, you will make carbon dioxide, which is a gas. It is very important that you are patient and add your sodium bicarbonate solution carefully. Otherwise, you may make a little volcano in your hood, producing a mess that you will have to clean up, like you see here on the right. When shaking your separatory funnel, you will be making carbon dioxide, which will build up pressure in your separatory funnel. As a result, make sure you vent often to prevent dangerous buildup of pressure. Along those lines, when venting, or even just when shaking, do not point the separatory funnel at anyone, so that any gas that is released does not impact your fellow students. That brings us to the end of this webcast. To recap, the mechanism of a substitution reaction depends on the type of leaving group, the strength of the nucleophile, and the solvent. The stereochemical outcome of a substitution reaction is dependent on the mechanism. For the concerted SN2 reaction, you get inversion of stereochemistry, whereas in the stepwise SN1 mechanism, you go through a flat carbocation, resulting in a mixture of stereochemical products.